Hello and welcome everyone to this new video on divergence theorem. In this theorem, we'll be talking about what is the statement of divergence theorem, and then we'll go into some critical problems. Okay, so the statement is saying that triple integral over a given volume of divergence of f is same as double integral over the surface which that volume has been creating of f dot n cap, where n cap is the outward drawn unit normal. Okay, so this is the basic statement of divergence theorem. So we'll be utilizing this statement and we'll do some problems. So let's quickly look at our first problem. It is saying that verify divergence theorem for this given vector function taken over the cube, where the cube is bounded by x0, y0, z0 up till x1, y1, z1. Okay, so here the volume has been created by a cube and the surface are the 6 surfaces of the cube. Okay, so we have to verify divergence theorem. That means we have to find the left hand side also, right hand side also, and show that both are equal. So let's quickly start with the left hand side of divergence theorem. The left hand side of divergence theorem is saying triple integral over the volume V of divergence of f. This is the LHS of divergence theorem, right? So first we need to find out what is the divergence of f. Okay, now let's quickly recollect that this operator stands for I del del x plus j del del y plus k del del z, right? Now this dot product with the f vector, so divergence of f, that would be, so basically I cap will be multiplied with I cap, that would be 1, and rest of the multiplications with the I cap will be 0. So I cap with I cap is 1, so we have 3xz and the del del x operator. So del del x of 3xz, that's going to be 3z, right? Similarly, if I show you with a different color, next I have j cap with j cap, so it's del del y of y square, and that's going to be 2y, so plus 2y, and finally we have k cap with k cap, so del del z of minus 3yz, and that would be minus of 3y. So that's our divergence value, divergence of f. So let's plug that value over here and we are going to get something like this: 3x plus so plus 2y and minus of 2y, they would be ultimately becoming minus of y dv. Okay, so this is the integral that we are going to find out. So now when we talk about a cube, it's going to look something like this, and let's say this is our one of the axis, this is one of the axis, and this is one of the axis. Let's say this is x axis, this is y axis, and this is the z axis. Okay, it's given that the range of x, y and z are all starting from 0 and going up till 1, right? So that means all these directions, all these lengths are 1 unit, this is 1 unit, and this is 1 unit, right? So the length, breadth and height, everything is 1 unit because it's a cube with length 1. So it's going to be very easy to do this triple integration. The limit of x is 0 to 1, y is 0 to 1, z is 0 to 1, and my function is 3x minus y of dx, dy and dz, right? So that's going to be a very simple integration. So first let me integrate with respect to x, and if I integrate this with respect to x, I'll be having 3x square by 2 plus xy, sorry, that's a minus xy, where x limit from 0 to 1 dy dz, right? So if I plug in the limits from 1 to 0, if I put the upper limit, which is 1, I will be having 3 by 2 minus y, and if I put the lower limit, it's going to be 0. So remaining is dy and dz. Again, we proceed with the integration in the same manner. If I integrate this with respect to y, I'll be having 3y by 2 minus of y square by 2, the limit of y from 0 to 1 dz. If I put the upper limit, I'll be having 3 by 2 minus half, and if I put the lower limit, that's going to be 0. So basically I have 1 over here. 3 by 2 minus half, that's 1, right? So integration of simply dz, that's going to be z, where z from 0 to 1, and so my final answer is 1. Okay, so I have got the left hand side of divergence theorem, the calculation part, I've got the answer 1. Now since this is a verification question, I will be trying to find out the right hand side as well and try to show that the right hand side is also giving me the answer 1. Okay, now calculating the right hand side, it's a little bit lengthy. Okay, so just be patient. Now coming to the RHS part of divergence theorem, that is double integral over the surface S f dot n cap ds, where n cap, as I told you, it's the outward drawn unit normal. Now what's that? We'll come to that very quickly. Let me just draw the cube once again. So let's say this is my x-axis, y-axis and z-axis. Now, how many surfaces does this cube have? Obviously, you can understand there's a top surface, which is surface number 1. There's a side surface. There's another side surface. So 2 more side surfaces, 1 at the bottom. So that's going to be 4 surfaces. The one at the back, which is the screen, and the one at the front, right? So there are total 6 surfaces. So we need to do this integration for all the 6 surfaces. Now for convenience, just imagine I have the same cube right over here. Okay, so I've just made this cube for you guys. It's for a better understanding. So this is a cube. Imagine this is a cube of unit length. Okay, so all the lengths are 1 units. Now imagine this is the x-axis. I hope it's properly visible. There's an x-axis on this side, there's a y-axis on this side, and if I little bit rotate this, then this is the z-axis right over here. Okay, so I have all the 3 axes, and this is the cube that I'm talking about over there. Okay, now see, I have named the surfaces. This is the S1 surface. Right behind of this surface is the S2 surface. Okay, then so I have the S1 at the front, S2 at the back, and on the side I have S3, and on this side I have S4. On the bottom I have S5, and on the top I have S6. Okay, so I have all the 6 surfaces. I want to do the integration for all the 6 surfaces separately. Let's start our calculation for the S1 surface, which is double integration over S1. Okay, now what's the n cap value? Finding the n cap is the essential part. For the n cap is the unit normal, which is outward drawn unit normal from the surface. That means if this is S1, I take an arrowhead. Okay, so this is an arrowhead. I take an arrowhead and I put it right perpendicular to that surface. Okay, I put it perpendicular to that surface. Now if I can move it anywhere on the surface, does not matter. Let's say if I keep this point over here on the S1 surface, so you can see this is basically parallel to the z-axis. You have the z-axis right over here, right? You have the z-axis over here. So this is now just parallel to z-axis, but in the opposite direction. You can see the arrowhead is in the opposite direction of z-axis. Okay, the direction of z-axis is given by nk cap. So here n cap is the opposite of z-axis, so that's a minus of k cap, right? Now I need to do f dot n cap. So let's quickly bring our f function. Our f function was as you can see, it was 3xz plus y square minus 3yz. So I'll just bring that. F function was 3xz I cap. Okay, so we have got our f vector and the n cap vector. So what would be f dot n cap? Okay, so k cap multiplied with k cap with a minus sign and a minus sign over here. So I would be having n cap minus k cap with this k cap. So it would be 3yz, right? So it's 3y. I won't write it directly. So f dot n cap is 3yz. Okay, now let me again come back to the cube over here, the S1 surface. Okay, what's the equation of the S1 plane? I need the equation of the S1 plane. See, on this plane, if I move my finger on this plane, can you say which variable is not changing at all? Okay, see, this is the x-axis, the y-axis. So if I move on this plane, x values and y values are continuously changing if I move my finger. But which value is not changing? The z value, right? The z value is not changing. And right on the S1 surface, which is connected with the origin, the value of z is nothing but 0. Okay, so on this plane, the z value is always 0, even if I move my finger. Only the x and y values are changing. So the equation of the S1 plane or the S1 surface is z equals 0, right? So I have z equals 0 on the S1 surface, and if I plug that in over here, so I'll be getting 0 as my f dot n cap, right? So for my S1 surface, the f dot n cap value is 0 ds, right? So that's pretty much nothing to be done. The value becomes 0. Now let's move on to our S2 surface. Okay. Achha. Now again we have to figure out what is going to be our n cap, right? Now again coming back to the surface, so this was S1, S2 was the one which is completely on the opposite side, right? This was my S2 surface, completely on the opposite side. So now if I take my n cap, you can see if I take my n cap, so it's obviously, you can see it's in the direction of the z axis, right? If I place my n perpendicular vector over here, so that's completely parallel to the z axis. So that means n cap is now going to be k cap. Okay, and what's the equation of the S2 plane? See, on the S2 plane, now again it's basically the opposite side, we have xy axis. So here again, if I move my finger on the S2, the x and y values are changing, the z value is not changing, and the z value is fixed to how much? See, how much distance have I moved from the origin along the z axis? I have moved 1 unit distance because it's a cube of length 1. So I have moved 1 unit distance over here. So on this plane, if I move my finger, xy values are changing, the z value is fixed to 1, correct? So the z value is now fixed to 1. So f dot n cap, if I find that out, f dot n cap is now going to be minus 3yz, and if I plug in this value of z, it's going to be minus of 3y, correct? So minus 3y. Now on the S2 surface, which variable is fixed? The variable z is fixed, its value is z equals 1. So the remaining two variables are x and y. So we are going to have dx and dy, and instead of writing S2, you can understand it's better to write x varying from 0 to 1 and y varying from 0 to 1, because we have dx and dy, z has been fixed to 1, correct? Now moving on to S3. So on the S3 surface, now I need to find out what is my equation of the plane and the n cap. So for the S3 surface, now if I take the n cap, the direction of n cap, which I place it on the S3, so you can see that's nothing but just parallel to the x-axis. I have the x-axis over here, so this is parallel to the x-axis, and you can understand it's in the opposite direction of x-axis, right? X-axis is this way and the n cap direction is that way. Okay, so that means the n cap is minus of I cap, And what's the equation of the S3 surface? See, on the S3 surface, it's connected with the Z axis and it's connected with the Y axis. So if I move my finger on the S3, my Y value and my Y value on this axis and the Z values are going to change. What is not going to change? The X values are not going to change since it's connected with the origin. So on this plane, X value is 0, right? So I have X equals 0 on this plane. So if I calculate f dot n cap, that's going to be minus 3xz, and if I put x0, then that's going to be 0. So this is again 0 ds3, so I don't need to specify my s3 over here. I'll be moving on to s4. Okay, so now for the s4, again look at the plane. For the s4, it's just completely opposite of S3. So whenever you're coming to the opposite surface, what's happening? We have done that before. When I'm moving on to the opposite surface, I'm moving 1 unit distance and the direction of n cap is just becoming opposite. So that's going to be plus I cap. So that's a clear understanding. So if we put those values over here, it's going to be plus 3xz, and if I put the value x equals 1, that's going to be 3z, correct? So we are having 3z. Achha. Now on this plane, x value is fixed, that is 1. So the remaining variables are dy and dz. So you can understand that y is varying from 0 to 1 and z is varying from 0 to 1, correct? So we have done for the 4 surfaces. Now moving on to the 5th and the 6th one. So plus double integration over S5. Okay, so again take a look at S5. So this is the S5. You can see it's connected with the x-axis. It's connected with the x-axis over here, and it's connected with the z-axis over here, right? So we have the S5 like this. So if I take my n cap, that's parallel to which axis? It's parallel to, you can see it's parallel to the y-axis, right? This is the y-axis. So for the S5, this n cap is parallel to the y-axis and it's in the opposite direction. So that means minus of j cap. And on this plane, which is the fixed variable on the S5 plane, x and z values are changing, y value is fixed since it's connected with the origin. So y value is 0 on this plane. Okay, so this is going to be minus of j cap, and the value of y is going to be 0. So if I calculate that, f dot n cap, that's going to be minus of y square, and if I put the value of y equals 0, it's going to be 0. So that's again 0 ds5. And finally coming to the last one, so you can understand when I'm going to the S6, when I'm going to the opposite side, just the unit distance is going to get added, it's going to be 1, and the direction is just going to change, so it's going to be plus j cap. So this is going to be plus y square. If I put the value of y, and that's going to be 1, right? So my function over here is 1. Since y value is fixed, the remaining variables are x and z, so dx dz, x 0 to 1 and z 0 to 1. So these are all the 6 integrals that we have got. The first one, the second one, the third one, the fourth one, fifth one, and finally the 6th one. So we need to add up all these 6 integrals and we should get the same answer as that of LHS, which was 1, right? So let's start doing the calculations. I'll use a different ink for clear understanding. The first one is 0. Okay, so I'll write the first one is 0. The second one, if I integrate this for the first integration with x, if I integrate this with x, then I'll be having minus 3xy, right? Minus 3xy. I'll just skip jump. I'll be having minus 3xy, x limit from 1 to 0. So if I put the upper limit of x, it's going to come back to 3y again. So it's basically going to remain minus 3y, y limit from 0 to 1 dy. So I've just done the first integral with respect to x, and we don't have a change because x is not involved here and the upper limit is 1. The third integral is 0. The fourth integral, again if I integrate this in the same manner, okay, integrate this with respect to y, the first integration, then we will be having 3yz, okay, and if I put the upper limit value of y, which is 1, I'll again get back 3z. So I'll be having plus integration z0 to 1, 3z dz. Then the fifth integral is 0, and finally for the sixth one, so that's a constant 1, so it's unnecessary. So x0 to 1, z0 to 1, whatever we integrate, the value we are supposed to get is just simply 1 after doing both the integrations, right? So I'm directly writing that as 1. Okay, so the remaining ones, if I calculate, this is going to be minus 3 by 2 y square, y value is 1, so I'll directly put the value, plus this is going to be 3z square by 2, so 3 by 2 and z value is going to be 1, plus a remaining 1, and these two are going to get cancelled, and we are going to get is 1 as the final answer, which is same as that of the LHS, right? So we have verified divergence theorem. Okay, now we'll move on to a little bit more critical problem. This one was easy, little bit easy. Moving on to our next problem. Now in this problem, it's saying that evaluate this over the entire surface of the region bounded above the xy plane by the cone z square equals to x square plus y square and the plane z equals to 4. Now what does that mean? I have to find out this integral which is above the xy plane, okay, and which is the surface is the cone and it is bounded by the z equals 4 plane. That means if I try to draw the figure, let's say this is my x-axis, my y-axis, this is the z-axis, and if this is the value 4, z equals 4, then the cone is going to be something like this. Okay, so that's going to be a cone, and the height of the cone is 4 units. Okay, so that's bounded by the plane z equals 4, and the equation of this cone is given by z square equals x square plus y square, which is, as you can see, above the xy plane. Okay, and we need to find out this integration. So we know by divergence theorem this integration is equals to triple integration over the volume of the cone, divergence of f dv. So that's what we are going to do, because this is something that's going to be easy. Okay, so we are not going to do the LHS part, we are going to do the RHS part that I've written over here, because that calculation is going to be easier. Finding the n cap is going to be a little bit troublesome for these kind of things. Okay, so now when I'm talking about a triple integration, the problem is going to be to understand how the limits are going to change. Okay, so the same thing, just imagine the same thing is right over here in front of you. Okay, so this is the cone that we are talking about. Imagine the blue one is the x-axis, the red one is the y-axis, and this coming up is the z-axis. So you have the cone like this. Okay, so the cone that I've drawn here is right in front of you, and if I place this on my hand in this manner, then my hand is nothing but the xy plane. So you can see the cone is above the xy plane and it's cut by z equals 4. So you can understand the topmost point is basically z equals to 4. Okay, now if I slice, if imagine I have sliced the cone somewhere from the middle, and if I slice it right from the middle, then what you will be seeing is from the top view is going to be a circle, right? So if I slice the cone anywhere in the middle, then if you look at it from the top, you're going to see something like this, which is always a circle. Wherever I slice it does not matter, right? Wherever I slice the cone, you're always going to see a particular circle, right? So imagine I have sliced the cone somewhere over here. Okay, so I have sliced the cone somewhere over here, and that's a circular part, and if you look at it from the top, you're going to look at it like a circle. So if you are looking at it from the top, then this is the x, this is the y, and this is the circle that I have just drawn over here, right? This is that particular circle. Acha. Now we are going to try to put the limits. So once I have got this in place, I'll try to put the limits. The equation, okay, the equation of the cone is z square equals x square plus y square. Let's do one thing. Let's try to find out x from here. That's going to be plus minus of root over z square minus y square. Okay. So any point on the plane, any point on the actually the cone, if I take this point, let's say this point and this point, any point on the cone, the x values are given by something like this, plus root over z square minus y square to minus root over z square minus y square. So that means any point on the cone at any particular height, the x value, the value on the x axis, which is on the blue line, it's given by something like that. So x, I can say x is varying from minus root over z square minus y square up till root over z square minus y square, positive root over z square minus y square. Correct? I am finding out the divergence a little bit later. Let me just find out the limits first. Okay, now I'll be coming to the limits of y. Okay, now there is an easy way of doing that and there is a conceptual way of doing that. First let me explain the conceptual way, then I'll come to the easier way. Okay, now imagine I have taken a small bar over here and I'm going to move this straight line, this strip that I have taken. I hope you can see a small strip. I'm going to move that up and down, okay, up and down the circle and generate the entire area of this circular region. Okay, generate the entire area by just moving that particular straight line. So imagine this is the circle which you are seeing from the top. Okay, and I have taken one small strip over here, okay, and I'm moving that strip up and down to generate the entire area of the circle. Okay, now you can imagine that small strip which I've taken over here, that small strip is given by something like this. Okay, since I have done my first integration with respect to x, so that means I must have taken a horizontal strip and not a vertical one. Okay, considering x-axis to be the horizontal one. So I've taken a horizontal strip and now I'm going to move this strip up and down, okay, which I was talking about over here, to generate the entire area of this particular circular strip that I have taken. Okay, so what's the maximum point to which I can take this strip? The maximum point I can take it over here, the minimum point is over here. Okay, now at the minimum point, that means at this point, what is the value of x? X value is 0 because it's coming on the x-axis. It's just on the y-axis. Actually this value, it's on the y-axis, that means x value is going to be 0, and at this point also x value is going to be 0. Correct? So at these 2 points x value is 0, so you just plug that x equals to 0 right over here. Okay, if I plug that value right over here, x equals 0, then I'm going to get plus minus root over z square minus y square equals 0, and from there I'll be getting the value of y to be plus minus of z. Correct? I'll do a whole square, then I'll take y square equals z square. From there I'll get y equals to plus minus z, right? So y limit is from minus of z to plus of z. Okay, so I am moving this strip up and down to generate this entire area. That means I have generated the area of this circular strip. Now I'm going to move this circular strip up and down to generate the entire volume of the cone. Okay, so firstly I generated the area of the circular strip. Now I'm going to move that up and down to generate the entire area of the volume of the cone. Okay, now generating for the entire volume, z value is moving from 0 and the height of this is 4 units as already told before. So I'm going to move the z variable from 0 to 4. So this is how we get the limits. Okay, now there is a shortcut way of getting it also. Okay, now that does not involve the actual concepts that are running behind this. The shortcut is, first from the equation you get the value of any particular variable, let's say x, y, z, whichever one you want. So you get the value of x in terms of the other variables, you put that from minus of that limit to plus of that limit. To get the limit just for the next variable, if I'm going to write for the y variable, then take y equals 0. Okay, if I take y equals 0, then what remains over here? I will have minus of z. So that's the limit right over here. And similarly over here, if I put y equals to 0, then the entire value of this thing is going to be plus z. So that's kept just over here. And z, you can understand, it's varying from 0 to 4. So that's a faster way of understanding. First you write the inside limit, then you put one of the variables 0. If you're putting y 0, then you're going to write the limit of y. So you put y 0 and what you get is z. So you get y equals z. If you put y 0 over here, you get minus z. You write minus z over here. That's a shortcut way, but the actual thing happening is I have done right over there. Okay. Now coming to the divergence part. Okay, so I'll just erase off these figures right over here, and these calculations won't be required anymore. Now coming to divergence of f, the f is given to me right over here. If I take divergence, that means I have to do the partial of the I cap coefficient with respect to x, partial of 4xz with respect to x, partial derivative will give me 4z. Partial derivative of xyz square with respect to y will give me xz square, and partial of 3z with respect to z, that will give me 3, and I'll be having dv, or I'll write just dx, dy and dz, right? So that's our integration that we have to do, and whatever value we'll get, that will be the required answer. So let's continue with this calculation. It's going to be a little bit lengthy calculation, so just bear on. Z equals 0 to 4, y equals minus z to z. Now see, this integration, always be careful. If you have minus of something to plus of something integration, think about even functions and odd functions. Okay, so here I'm integrating with respect to x. Okay, initially I'm integrating with respect to x. With respect to x, you can observe that this is a constant, right? 4z is a constant when I'm integrating with respect to x. So that means this is an even function. Similarly, 3 is a constant, so it's an even function. We know constants are even functions. What are even functions? F of minus x is equals fx. That's an even function, right? And integration of the middle term, here again z square is a constant, so you're basically going to integrate x. So x is a odd function, right? So what is odd function? If f of minus x equals to minus of fx, that's an odd function, right? And we know integration of an odd function, minus a to a, integration of any odd function, that's going to be 0, and minus a to a, integration of even function, that's going to be 2 times 0 to a, whatever function is there, right? So these were the properties. Integration of minus a to a odd function is 0, integration minus a to a even function is 2 times 0 to a whatever function is there. Okay, so let's just incorporate that over here. So for the first function, it's an even function, so I will write, let's keep it minus z to z, integration 0 to root over z square minus y square and a 2. So 2 times 0 to a, 4z. The middle integration is going to become 0 since it's an odd function. So middle integration is 0. The last one is again going to be 3 times 3 of 0 to a. So I have just incorporated the 2 in front, dx, dy and dz. Okay. So now the integration has become much more easier. So I'll be getting if I do this integration, I'll have 8 of x. I'm doing the integration with respect to x, so it's going to be 8 root over z square minus y square. I'm putting the upper limit. The integration is going to give me x, and putting the upper limit, it's going to be this value. 2 into 4 is becoming 8, plus 3 into 2 is going to become 6, and I'll be having, achha, there's one z I have missed out over here. There's going to be a z, 8z, the z is already there, and then the upper limit, so 6 into the upper limit z square minus y square of dy and dz. Okay, so now we are going to do the integration with respect to y. So the first integration is done. Now again, let's see if there is any odd function and even function. Since we have a minus a to a limit, as you can see, with respect to y, z is constant, so we don't have to think about that. This is an even function and this is as well as an even function, right? So these are both even functions. That means f of minus x is going to be f of x for these two, right? The minus is going to get absorbed in the y square. So I can write it as z equals 0 to 4, y from 0 to a. Instead of minus z to z, I have taken 0 to z, and I'm taking a 2 outside. So 2 times 0 to a. If I take the root over z square minus y square common from both the terms, then I'll be having 8z plus 6 dy dz. Now this is the integration that we want to do. Okay, so basically over here, this is nothing but a constant. Okay, this is a constant with respect to y. So I'm just going to integrate this portion. Okay, integration of this thing. Now that's a direct formula. I hope you people know the formula. So I'm going to bring the constant outside, and also you can observe I can take a 2 common from here. If I take a 2 common, there's already 2 outside, so that's going to be a 4. And if I take a 2 common, that's going to be 4z plus 3. So that's coming out of the integration. And now I will be integrating this part. Okay, integration of this with respect to y. I hope you remember the formula. It's going to be y by 2 root over z square minus y square plus the constant square by 2. Here the constant is z, so z square by 2 sine inverse the variable by constant, which is y by z, and the limits are 0 to z. Okay, y from 0 to z, and the dz integration is still remaining. Okay, so if I now put the limits over there, I'll take the 4 outside as well of the first integration, 4z plus 3. Now putting the upper limit, you can see if I put the upper limit z in place of y, it's going to be 0. If I put the upper limit over here, so the first value is 0, the next one is sine inverse of z by z, which is 1. Sine inverse of 1 is pi by 2, so I'll be having z square by 2 into pi by 2. Okay, and then if I put the lower limit, okay, if I put y equals 0, then that's again a 0, so minus lower limit. If I put y equals 2, y equals 0, then that's again a 0, so there's nothing to write. Okay, and finally dz. So if I just simplify this a little bit, it's 4z0 to 4, and this value is I can get this pi by 4 completely outside. It's a constant, so pi by 4, I'm taking it completely outside, and the 4 is going to get cancelled, and what I have is z square 4z plus 3 dz, right? Now that's a very simple integration. So pi times, if I integrate this, first of all I'll multiply the terms and then integrate. If I multiply, it's going to be 4z cube. So integration would be 4z4 by 4, and the next multiplication is going to be 3z square. So that's going to be 3z cube by 3, and the limit of z is 0 to 4. Okay, and now if I just plug in the value, so the 3 and the 4 is going to get cancelled. So pi times 4 to the power 4 plus 4 to the power 3. If I put the lower limits, that's going to be 0. So if I just calculate this, I think it's going to come up to 320 pi. Okay, and that's our required answer. Okay, so that's how we deal with divergence theorem. I hope this video was helpful to you. Thank you, and I'll be back with many more videos.